So I will give you kinematic equations. So when students hear kinematic equations, they feel afraid, but I won't be asking you to know it's in very detail. So acceleration is constant in our situation. We are learning simplified conditions, and so far we've been dealing with and we are still dealing motion in a straight line. It's also one more simplified condition, that motion in a straight line. Last lecture and this lecture we're dealing with motion in a straight line. So acceleration, now it is speed is v initial plus a times t. So how we obtain this equation? So this equation can be obtained by, this speed is increasing linearly, because this equation is equation of a straight line. So this is yx b plus kx. So this is equation of a straight line that you have learned at school. So x is instead of t. Here, these are t's, and x. A is a constant. We have constant k. V initial is some other constant. This is b. So it's equation of a straight line. So vt is increasing linearly. In the case that all things here are positive. And this equation, as I've written for you, that v is delta s divided by delta t. A is delta v divided by delta t. So we can get rid of these deltas in simplified situations. So we can write s divided by t, and a is v divided by t. And by deriving the formula of v from this equation, we get a times t. Just multiply this with cross. So here is 1. So v is a times t. Okay, now xt is x initial plus v initial half a t squared. So this is coordinate or position. If you knew integrals, you would integrate this, you would get this. Integrate acceleration, you would get speed, velocity. If you integrate vt, you would get distance, and from distance you could basically say integrate velocity, you will get this coordinate or position. So this is this equation you will derive during mathematics. So we can derive it with integrals, but I assuming that you are learning parallel to this course, you are learning mathematics, so you probably haven't learned that yet. So we will learn maybe after 2 months or something. And this is st, distance. So acceleration velocity are vectors in general. They are vectors, but sometimes we can manage with speed only. Coordinate or position as well as distance, they are scalars. So now imagine you throw the ball up in gravitational field. In gravitational field, throwing the ball up in gravitational field. Let's draw a human being here, small human being. He's throwing the ball straight up, motion in a straight line. So straight up, he's throwing the ball straight up. Y-axis is also straight up. V initial is not 0, it's higher than 0. Now what is happening with G? Acceleration is held less than 0. So that's what it's happening, because when you have Earth and you have some kind of object, Earth is pulling the object down. So the force is in this direction. Force is mg. So it means that acceleration g has to be down in this direction. So depending on the vector, the direction of the vector, it can be, the vector can be held plus or minus. So depending on its relation to y-axis direction. So in this case, y-axis is up and the g is pointing downwards because force is pointing downwards. Force and the direction of force and acceleration have to coincide. So g is pointing downwards. So it means that g is decelerating v initial. So it's everything is okay, because as we have drawn here, g is decelerating. So 30, 20, 10. So v initial is 30, then it's decreasing to 20, then it's decreasing to 10, then to 0. So it means that everything mathematically is okay. So now what? Now we will make graphs. So g is negative. G is negative and it is equal to minus 10 meters per second square. So now let's draw the graphs. And here we have acceleration, here we have t, here we have 0. So here we have at, it is equal to g, and that is constant. That is constant, so we have straight line here, it's negative. Minus 10 meters per second square. Minus 10. Negative. Okay? Negative. What is here I am giving you the component a y component in y-axis. So it is a y component of the acceleration, because here is y-axis, but I'm just stressing you this because here acceleration is just it has only one component, but in more difficult ways, more difficult situations, there can be more components. So gravity is dealing only with y component. Here we have 0, we have this, we have Vt, and this is t. So V initial is something, some kind of, let's say 30 meters per second, and then it does what? It decreases. When the ball is going up, it decreases. V initial decreases, as we have shown, from 30 to 20, from 30 to 20 to 10 to 0, as our we had that example. Now this graph here is 0, it is xt, it is t, and this is x initial, and what's happening? X initial, then motion, sorry, here has to be t, motion in a straight line, and then it's saturating somehow, it's curved. So let's make this a bit more curved, so it should look like this. Increases in a straight line, then it curves. Here it is also Vy component. There can be many components, but here we are showing Vy component, but there is no x component because motion is the vector is straight up. So I'm just specifying you this. Equations are the same, like here. A is constant and negative, yes. V initial is just V initial, and acceleration is negative. Acceleration A or G, doesn't matter, is negative. So it is decreasing here. This equation is the same here as V initial is positive, T, A is negative because A is G and it is negative here. So here we can stress this minus that G is negative here. So here G is negative, we show y-axis is up. Now if you throw the ball down in gravitational field, what happens? In this case, you are standing in a balcony and you throwing the ball straight down, throwing. So y-axis is up, direction is up. V initial is considered to be less than 0, is considered to be negative, because here is V initial is going to the direction of y-axis. Here is V initial going to the direction opposite to y-axis, so it's considered to be negative. Although you're throwing 30 meters per second, but it's considered to be negative. A is considered also to be negative. So here is the, this is a bit too close. Here it is AT. This graph is from AT, and as previously, AT is, or G, AT is constant, it's equal to G, and it's equal minus 10 meters per second square. So the same here, negative. So what's happening with speed? So we said that speed is, these are y components. There is only y component, but in more complicated motion, there can be more components. So, but 0, V initial is what? Something, but it's negative, and then it is decreasing. Decreasing because G is negative, so V is decreasing. So and xt this is t, this is 0. Xt is x initial, and here it is curved and decreasing to 0 because it falls down on the ground. Yes. So here are the graphs, equations and graphs. What's most probably confusing for you that G is negative, so G is, you see, the direction is chosen according to y-axis position. Y-axis will always be from, it can sometimes be, but I have not encountered this situation. Y-axis is always up. You throw the ball up, so y-axis and the direction of y-axis and acceleration coincides, so it means that V is positive. Y is up, G, direction of G is down. Earth axis, as we have drawn here, as we have shown here, it goes down, so G is negative. G is negative, and from that we would, according to these equations, we draw everything. G is negative, V initial is decreasing, X initial it increases linearly, then it's slowing down because speed decreases to 0. Here what's happening, Y, direction of Y is up. Direction of V initial is negative because it's opposite to Y. Direction of so V initial is negative. G, let's write G here. G is negative because as the same as here, its direction is going down and it's opposite to Y direction. So in case of free fall, V initial would be 0. The initial would be 0 in case of free fall. But just imagine that you throw with some kind of some kind of initial speed non-zero to the ball from the balcony. Let's say this, but you throw it straight down, because here it's motions in a straight line. Okay. What else? Other thing is what if you throw the ball to the horizon? Throw ball to the horizon. It's moving. It's moving not in a straight line. The motion is not in a straight line. Motion not in a straight line. Okay. If you have y-axis, you have x-axis, y-axis, you throw the ball goes with velocity v initial, and the ball goes with trajectory of the ball is like this. It goes up, then it is reaches max height, maximum height. It is rising part, it is falling part. Here it reaches the ground. So we can split this V initial into Vx, and we can split into, and we can write this in two components, Vy, Vx and Vy. So because this V initial is not, the motion is not in a, not vertically up or vertically down, so then we have y and x components. And what's important that here gravity is acting, gravitation force. So gravitation acts or changes only Vy component. But it does not change gravitation, does not change Vx component. That's why in previous page I've given you that was y component. Because if you throw the ball straight up, ball goes straight up, what's happening? There is no x component, only Vy component. X component is 0. There is only Vy component is not 0. So that's why we were talking previously here about Vy components. Ay, Vy, so here it is G, A or G is the same. So that's it. Now what I want to tell you is about net force. So when we are speaking about F equals ma, we are speaking about one force, but usually because many forces are acting on the body, so we're speaking about net force. It's ma, net force, and all the forces acting on the body, they determine the acceleration and the direction that the body moves. So imagine you have an object. If the object is on the ground and the object is being pulled, so F pull. Also the object is being pushed, so F push. And also there is F friction that opposes the movement. Friction always opposes the motion. So here let's write it with red. Here we may write it with green. And here we may write it with, mark it with blue. So now what's happening? We add all the forces. So let's add F push. We add to F pull. So green and red, we add them together. What do we get? We get vector from here to here. So we get vector, we get this vector. So it is the sum F push plus F pull. So it would be this vector. the sum of these two. Now what we do, now we onto this vector we add this vector. So this is vector equal length and direction. So here, and now we make, and what's left is this part goes off because its friction opposes this brown vector, and this is F net. So you can see that this is the length defines the magnitude of F net, and the direction defines the, and this arrow defines the direction of net of this force and the acceleration and the motion, direction of motion. So later we will consider more examples like this, but let's say to determine F net force, you need to consider direction and strength of all forces acting on the object. Let's leave this on object. So this is the idea. There are examples that in the slides you can see examples. What example that I really liked was that there was a bow. Let's draw a bow. And the string is like this. Here it is an arrow, and it shows that the direction of force is here. Force is here, and the force is here. But the net force is the sum of these two forces, and its direction is the same as the arrow would go. Arrow goes in this direction because this is F net, and it is obtained from these two forces that the string provides. Yes, you push the string against its natural state, and then you let it go, and it provides the force F net from these two forces. So another one example was there was a bone, and there were three dogs. Let's draw some primitive dogs here. There were three dogs pushing this bone. Not pushing, but pulling this bone aside. So to each side. So now what's happening here? F net was given as it was 0. So there was defined as a static equilibrium. So what's happening here? We can show that this center of the bone is marked as the center. Here we have two forces acting here and here. So what happens? We just add these forces, and here we have forces, the sum of this and this. So this is, let's call F1, this call F2. So F1, F2, this is F1 plus F2, the sum, and this would be F3. This is F3. So because F3 is equal to this, to the sum F1 plus F2, F3 is equal. So net force is equal to 0. This is going up with some kind of magnitude. This is going down with some kind of magnitude. So equal in magnitude, but opposite in direction F3, and the sum of F1, F2. We will get this kind of laboratory work in laboratory work. This situation we'll have definitely this one. So okay, so thank you for listening, and we'll see you in the next lecture.